Ladies and gentlemen, he's almost ready, running out of the dressing room. Here he is to address his talk to you. Professor Mischa Dohler.
When you think of the internet today, you don't think of a computer A connected to computer B, B to C, C to D, D to A with a thick Ethernet cable. You think of Facebook, of eBay, of Amazon, you think of opportunities. That's what you think of. Now, with the emerging Internet of Things, we would love to get to the very same stage. We just love to forget object A connected to object B, machine C to D, robot E to A. Just want literally just focus on the opportunities. Now, as of 2014, however, we are still designing that Ethernet cable. You have heard a lot in this conference about the actual machines, about the robots, about the artificial intelligence in there. What I want to talk you through today is about the connectivity. This Ethernet we're building today, of course, it's not a cable. It's wireless. It's an advanced Ethernet. Ethernet plus as we call that. And it will show you essentially the road to all these opportunities we'll have maybe by 2020, 2025, the same as the internet today as we have started 20 years ago. Now, before I do that, I want to give you some examples of which type of machines are connected today. And when we talk, my community talks about machines, we talk less about robots. So that's too early for us. We talk about sensors. We talk about simple actuators. That's the type of machine we're thinking of. Now, the sensors which are out there instrumenting a wide range of applications. An example being very heavy industry. For instance, the oil and gas industry. Pipelines are being monitored. Or the roads and tunnels. So I founded the company World Sensing. You see the blue logo here, which is doing nothing but that. You wouldn't know about this, but when you drive through a tunnel, there are about 17 sensors every 100 meters, which you don't see. They're measuring essentially tilt, moisture temperature, torsion pressure, etc., just to make sure that safety is guaranteed. Now, these sensors used to be cabled. When they're cabled, it means you need to put up a lot of efforts to actually go there, install them, a cable cost, etc. So it's quite an expensive exercise. And coming along and say, hey, we're going to do that wirelessly is a major add-on to the industry. I'm very excited about it. Now, it's not as simple as it is because as the tunnel gets long, propagation is very complicated. And in addition, you have often hundreds, if not 200s, 300s, 400s of sensors connected, and you run very quickly into actually connectivity problems. So that's one thing of what the company we solve. But the value add is very simple. We lower essentially the capital expenditure by simply coming there and installing the data loggers and the sensors, and connectivity is just there essentially within a few seconds. An example I give you, we instrumented one of the largest harbors in the world when it was being constructed, and the company which came to install our sensors there prepared for a whole week of installation because they thought it's going to be cabling, putting cables, nails, etc. It's quite an elaborate process. In the end of the day, they were done in 2 hours. It was very quick. So you save a lot of cost by just going down from 1 week to 2 hours. Then you save a lot of cables. People love to steal for some reason cables. So a lot of copper in there, etc. So there's a lot of value these days. You get rid of that as well. So it becomes a very interesting value proposition for the construction industry. We're also in an interesting application as the oil and gas industry or the fracking industry, where it is all about, at the very, very beginning of the process, it's all about discovering where the oil is, where the gas is, where the minerals are, where essentially the fracking happens, where there's any problem, CO2 sequestration, you want to monitor that. What they do is they essentially take a picture of the subsoil. The very same way as we use our CCD camera, you have like millions of sensors in the CCD camera, but they would roll out tens of thousands of sensors essentially on the field, each separated maybe by 100 meters, 200 meters, over a field of 10 kilometers per 10 kilometers, and then they would use seismic waves, excite the earth with a big hammer, which goes as a big truck which goes, excites the earth. The seismic wave propagates, is being reflected, and the seismic array, these sensors which are deployed, pick it all up. Now, Before we came along, that was all cabled. Now you do the maths, 10,000 sensors is like the minimum shooting, and 10 kilometer per 10 kilometer, it's a lot of cabling. And the easy area is gone. So there's no flat area anymore to do these type of prospections. So it becomes a very elaborate process to bring all the cables there, etc. So we introduced the wireless solution, which immediately was also a value add there. Now let's move on a little bit to the area of smart cities. That's a pretty hot topic at the moment, and that's really all about making the city smarter, often using essentially real-time decision taking from sensors, whether it's temperature sensors, it's parking sensors, etc. And once you actually sit down, you do the business case, you figure out there are not so many business cases in a smart city, at least to bootstrap it. What you really would like to is to deploy that intelligent technology, whether it's a sensor, a simple actuator, which brings you also some revenues. And of course is useful to the general population. And you sit down, you do the calculus and figure out there may be 2, 3 applications in the smart city which fulfill that criteria. And number one is smart parking. So smart parking is where you put essentially sensors in each or almost each parking bay. And that sensor would be able to tell you whether a car is parked on top of it. So you know immediately which places are free, which ones are vacant. So that goes to your smartphone app or to your navigator. And instead of you doing rounds and rounds and trying to find a parking spot, you're being told, hey, don't go there, it's completely full. Go there, there's a place there and exactly where to park. Now that's the beautiful side of the coin. What is really paying the party here is, and let's keep this in the room here, is actually we can tell who paid for the parking and who didn't, because we can correlate occupancy with payment data. So we know immediately, hey, there's somebody who hasn't parked. There are 2 or 3 guys, who haven't paid. There are 2 or 3 guys who haven't paid really for their parking ticket. So we can tell the law enforcement, hey, there's an area where you really want to like to go and to check instead of running around randomly and trying to figure out who paid and didn't pay. And it turns out that that infrastructure pays within 8 to 9 months, which is unprecedented for street furniture when you roll out things in the street. So cities are very excited about it. My company, World Sensing, is one of the 2 pioneers in that field, along with Street Line Networks in California. So that's the smart city space. Another application would be actually car counting, traffic flux estimation. So we did a joint venture where we were able to count exactly how many cars go over the street. Instead of using loops, we would use sensors embedded into the actual ground. Then another company we just acquired is doing the journey time estimation. So when you drive, in fact, they're deployed in London. When you drive into London on the M4, for instance, and it says like 20 minutes to downtown London, that's their technology. What they're doing, they're using sensors to scan your Wi-Fi and Bluetooth addresses, put a hash on top, timestamp on top, central database, so we know exactly how much it takes to get from point A to point B. And that's very interesting because suddenly we can do what everybody's aspiring to do, a big data exercise. We got the static parking data and we got the dynamic flux data. We can correlate data. We know how many people come in, where they're going, what's the occupancy in the city. We can re-engineer this back into the traffic lights with simple actuators. We can actually control fluxes into certain areas, out of certain areas. And suddenly your city literally becomes very, very smart and the whole solution extraordinarily appealing. So that is a traffic part. Other applications are street lighting. So the city of Barcelona, for instance, pays about 3 million euros every year on the lighting. And just putting some simple sensors into the bulbs, actually, or close to the bulbs, you're able to control that and say, hey, between 2 and 5 in the morning when nobody's down there, just switch off the light and you save a lot of electricity. It's about 1/3 of that money, which can be saved. It's quite a lot of money for Barcelona. Other applications are water irrigation and parks in southern countries, etc. And that's about it. That's about it for smart cities, I'm afraid. There are a few little applications, but you will hear a lot about temperature monitoring. You will hear a lot about pollution monitoring. Yes, there is a business case, but it's very weak. Clearly, the business case would go through the insurances, maybe allergic people, etc. But it's a very long way to go, so there's no obvious first-order business case there. So it reduces very quickly to very few applications. Nonetheless, loads of sensors to be connected, and here's a challenge. How do you connect in a city like Moscow, in a city like London, millions of sensors? Okay, so now in Moscow we're going up to 60,000, very soon to 300,000 sensors. Nobody has ever done this before, and here we are. Wireless networking came in, and in the very early days, when we started to design that system, we understood these sensors, which will be in the pavement, will be somewhere in the building, etc., will have no electricity supply. So they need to live off batteries for a pretty long time. It's not as long as you think. So you see a lot of academic papers which claim it has to live for 10 years, for 20 years. It's not really true. So once you go to the industry, they're okay to change batteries every 2 years. It's no problem. They used to do that, okay? They have people in the streets, they have people in the field. So changing batteries every 10 years is a very long-term requirement. Of course, a lot of scavenging solutions come in, so it's just living perpetually for a very long time. But we understood that we need a solution which is essentially consuming very, very, very little energy. And that was a big challenge, because the only communication systems we knew as of 2000 were our mobile phones and all the legacy which came before. Now, a mobile phone, you know already, probably back then, you needed to recharge it once a day. My iPhone, I needed to charge it twice a day. Now, you can't do that, clearly, with a sensor. So we had to completely re-engineer the system. And we started, as a community, with designing these so-called low-power wireless systems. Zigbee being an example. So maybe some of you know of Zigbee. I don't presume everybody does. But Zigbee is a very low-power solution which would transmit at maybe 10 milliwatts, very, very little energy compared to my mobile phone, which transmits at 2 watt. Okay, so it's a factor 1,000 more, actually, my mobile phone compared to my Zigbee module. So we started designing that. We came up with a beautiful protocol stack over about a decade of work. Okay, a decade of work, loads of really, really clever engineers. We started with the physical layer. The physical layer is the layer 1 on the OSI scale there, which is responsible on the point-to-point connection. So it would really make sure that I can talk to you. And we have designed about 6 physical layers today. Okay, so 802.15.4, which Zigbee is using. I'll call it Zigbee. Strictly speaking, it's IEEE 802.15.4. Is using 6 physical layers. Okay, so far so good. They're pretty good. Then we started designing the MAC protocol, which is layer 2, which is the medium access control protocol, which makes sure that, hey, if more than one person wants to talk to me, we don't have problems here. Okay, so we had contention-based protocols, etc. It turned out it didn't work with thousands of sensors or hundreds of thousands or millions. So people started wondering, can we do better than that? And we came up with a very beautiful design, which is 15.4e, a little add-on here, which would synchronize the whole sensor network in time and in frequency. So every sensor would know when to wake up, when to communicate with its neighbor, and when go back to sleep. Okay, and the whole design has been done by a chap called Chris Pister from Berkeley, who founded a whole company out of that called Dust Networks, later bought by Linear Networks, the biggest silicon manufacturer in the Valley today. And when he started, when he came to the standards committee, everybody said, Chris, no way that you can actually synchronize thousands of sensors at almost no energy cost. Okay, because everybody, the academic knowledge is it's very costly to synchronize large networks. Now, Chris at that time didn't know that it is impossible, so he did it. Okay, so he built the whole system and standardized it, built a company around it, and made a fortune out of this. Now, that's layer 2. Then we figured out, okay, so these sensors now are able to communicate, but how do they communicate now with my internet? And the internet speaks one language, which is IPv6. So we needed to put IPv6 on these little devices. And the problem is that the packets we designed to go over the air were very short compared to the packets which go through the internet. So the packets which go over the air with Zigbee are about 100 bytes, and the internet packets about 1,000 bytes. So we founded the IETF group called 6LoWPAN, which would standardize the way how we chop up these packets, how we do header compression of the IPv6 header, which happens to be as long as a single Zigbee packet. So, and the group did a marvelous work, and the beauty of this is now that any sensor anywhere in the world can talk to any supercomputer on the other side of the world because they speak the very same language. Okay, and then we did a little patch-on work. We worked on routing protocols. So I was the founding member of a group called IETF Roll, where we designed a protocol called Ripple, which came out of the work I'd done with Thomas Wattain and France Telecom, which would allow us in a standardized way to essentially route data through the network, any manufacturer sensors talking to any other manufacturer sensor network, etc. So that's a beautiful thing of work. So we came up with this really gorgeous stack, which is operational today. We started using it, and we figured out it doesn't work. All right? So 10 years of engineering labor just showed us it doesn't work. So my company started using it. We started instrumenting essentially the equivalent of the Royal Albert Hall in Barcelona called Palau Sant Jordi, where we put out 400 sensors in the roof. We're monitoring the structure of the roof because, that's a true story, Lady Gaga gave a concert there and she hit a resonant tone and the whole structure was vibrating. They were really afraid the whole thing would just collapse. So they said, we need to instrument it. We won the tender because we were wireless, so we're cheaper, and we're instrumenting that thing now. Now, when we rolled out 15.4e, we ran really into troubles here, because there's no way literally you can support 200, 300, 400 sensors, not to talk about thousands or millions of sensors. So no matter how hard we tried, really, there was just no way out. So the brightest engineers all over the planet, with a lot of money from Silicon Valley, 10 years of engineering, we've just been going the wrong way. Okay? Broadcom realized that. Broadcom is the largest chip manufacturer in the world. They decided not to produce Zigbee chips anymore. Okay, end of the story. So I've been preaching this for 4 years now, 5 years probably by now, ever since I realized with my company that in the real world, that does not work. From an academic point of view, it's beautiful. Loads of degrees of freedom. You can publish a lot of papers and nobody can challenge you, but you can't actually make it work. So here you go. We did some mistakes. And mistake number one is, we didn't realize we don't need low power. We need high power, but we need low energy. Because power gives you range. And energy is what drains your battery. So can we have a system which is high power but low energy? It turns out we can. Remember, energy is power multiplied by time. So if we are able to design a system where the sensor just wakes up, the machine, whatever it is, sensor, actuator, robot, etc., wakes up for a very short time, sends a message, goes back to sleep, and I'm talking about a millisecond or 10 milliseconds here, and transmits at 2 watts, 4 watts, etc., like my mobile phone, I get an enormous range like my mobile phone has, whilst I'm not draining my battery. It can live on for years. Now, the first community to realize that was the Wi-Fi community. Wi-Fi, Gainspan came along. So Gainspan is a company in the US which said, hey, we can do that with Wi-Fi. Wi-Fi is not like cellular, but it's better than Zigbee. It's like 10 times more transmission power. Everybody knows about Wi-Fi. We've got good standards community, etc. And they said, hey, why don't we just push the standard .11, 802.11, just to the very edge where we can be, and we duty cycle my Wi-Fi systems as much as we can. And it turns out .11 has a word for that. DRX, duty cycling, okay? It was in there all the time whilst, the Zigbee guys were developing 15.4 stack. And then suddenly this camera comes along, the first Wi-Fi enabled, low power Wi-Fi enabled product, a camera, take a picture and upload it directly to the internet with a battery lasting normal bad time it lasts for taking pictures. Everyone's shocked. It's impossible. Yes, you can do it. If you really heavily duty cycle your electronics, you put it to sleep. There's nothing which is consuming any energy unless, of course, you switch it on, you transmit. And the beauty of Wi-Fi is once you switch it on, the data rate is so high that you get your JPEG picture, your movie over very, very quickly. Whereas Zigbee, the rate is very low. You have to wait. The time you wait, your radio's on, it consumes energy, and it turns out, and that was a big shock, that Wi-Fi is 10 times more energy efficient than Zigbee for the same type of file transfer. Okay? So we forgot about Zigbee. We all started working now like crazy on Wi-Fi. But Wi-Fi is beautiful for indoors. We know Wi-Fi. There's Wi-Fi everywhere on this planet. The only problem is I couldn't really use it for the stuff we had in smart cities. So we won the Moscow tender for the smart parking there. And of course, you couldn't ask the town hall to put up Wi-Fi base stations all over the place. Some cities have it, but not all cities have it. And the biggest discussion you always have when you put up street furniture like a Wi-Fi base station is, hey, who pays the electricity? Because the electricity typically is being paid by the guys who own the lamppost, which is the lighting department in the city, whereas we're using it for the parking department, and they wouldn't talk to each other, all right? So you have a very simple operational problem here. So we didn't use it. And that was a time when a new system was born. And that new system is called low power wide area network, okay? And the beauty here is that is a type of system which would allow you to communicate over kilometers, okay? Connect your sensor with that radio. It's heavily duty cycled as well, and it has another few magic ingredients and allows you really very long range. So today in Moscow we have, we could have gotten along with a single base station for the whole city center, but we put a few more for redundancy reasons. So we have connected all our sensors, which just works really beautiful. And to get you an idea on the range, my CEO, when he was landing in Paris, okay, he had a smart parking node in his luggage. It was sent an hourly ping saying I'm alive. That ping was picked up in Barcelona. 900 kilometers range, okay? If you do the calculus, it has a link budget of satellite systems. So it turns out that in fact, very soon, for anything which is not time critical, maybe the whole planet, the whole Internet of Things will just be connected to a satellite. You don't have to worry about coverage anymore. And that's beautiful. So when I was CTO at World Sensing back then, I thought, that's great. I don't have to worry about installing large amount of base stations. I don't have to worry about who pays electricity. Just put one base station, it covers my whole city, connects seamlessly my thousands of sensors, it just works, and I can concentrate what I really want to concentrate on, which is doing business, okay? So here you go. The reason it works so well is it's very simple. Instead of using 300 kilohertz of bandwidth or 2 megahertz like Zigbee or 20 megahertz like Wi-Fi does, they would just use 100 hertz. 100 hertz is extraordinarily narrow. So it takes some skills to build filters which are 100 hertz, etc. But we've been doing this for the past 200 years, 150 years probably. So we know how to do it. And once you're down to 100 hertz, you cut out all the noise. And that's why you get these link budgets of 150, 160 dB to those who are skilled in the arts, and it means something. So that's essentially the interesting thing. There's a company called Sigfox, which is doing that. There's another company called Sigcleo, which was bought by Semtech by now, founded by one of my dear friends from France Telecom, which is using very long CDMA spreading sequences. So it works like 3G, but with codes which are much longer. So it gives you essentially the link budgets you really need to connect the machines. The problem of that system is it is actually proprietary, okay? So which is not a big deal today. Big surprise, particularly to me it was. I love standards. I've been part of the standards community for now 10 years. But it turns out that a lot of IoT projects today, a lot of projects where you need to connect machines are very large. And the city of Moscow really doesn't care whether you use a standardized or non-standardized system as long as it works. So essentially, we said, hey, we need to see how to actually scale into the 21st century using technology which would really last until 2020, 2030, 2050, and would be able to connect our 50 billion or 50 trillion little sensors, machines, objects, etc. And this is when the cellular community woke up. Okay, so the cellular guys, essentially the same community which is designing mobile phones we use today, said, hey, we can do that. We can do that. And There was a bit of an outcry at the very beginning because it seemed like totally implausible that we could use the very same system which we use to do phone calls, we download data, to essentially put them into sensors, which would last for years in battery, which would transmit just a little bit of data, mostly uplink. Okay, it's just the bits and bytes. So my parking sensor is just saying yes or no. It's 1 bit. You encrypt it, 64 bytes. That's it. A little ID on top. So it's not a big deal of data, but there are billions of those. Okay, so we sat down in the community and we said, hey, can we do that? And it turned out to be trickier than we thought. Okay, so loads of issues with the power consumption because here we really consume 2 watt or 4 watt once we transmit. So you have to do your job very, very quickly. I'll explain you in a moment where we are today. The other thing was a delay. There's a lot of time-critical stuff happening, etc. So the whole community is working on this now. Etsy M2M started, actually probably 3GPP, which is standards body responsible for standardizing mobile phones, were the first one to look into this in a very simple way. Then Etsy M2M, which I was founding member of when I was at France Telecom, started working on this today as well from the architecture point of view. Today 3GPP is working on that. A lot of standards body now trying to really come to terms with a standardized cellular machine-to-machine system. Now, they don't call it machine-to-machine, actually, so you wouldn't see that in 3GPP language. They call it MTC, for machine-type communications. Exactly, that's what it is. So where are we today? Well, we can't do it yet. As much as we'd love to, we're not there yet. The biggest problem is, and you will realize it when you switch on your phone when you step off the airplane, it takes a while for the phone to find the cellular tower. Okay? Sometimes it's done like in a second, sometimes it takes 2 seconds, sometimes it takes 4 seconds. We'd love to do it in a millisecond or 10 milliseconds, okay? And the process is exactly the same. The sensor is sleeping. I remind you, it's sleeping probably the whole day, except when it sends a message saying, hey, you know, my smart meter has changed, that's the value, or my parking place has changed, etc. It needs to be done very quickly. And the reason it takes so long is because you need to go through the contention procedure of 3GPP. How does it work? It's a ping-pong game between your mobile phone and the base station. It says, my mobile phone wakes up and says, hey, you know, I want to make a phone call now. I'm choosing one of 64 random codes. I'm sending it to the base station. The base station receives it, say, hey, okay, I received a code here. That's, you can now transmit, I got it. Then my next message up is saying, that's my temporary ID. Sorry, that's my ID. That's what I want to connect for. The base station gets that message, says, okay, I'll let you connect now on the data channel where you can transmit the data, the voice call you want to do. So we're playing ping pong. Takes a lot of time. And I'm not the only one talking the system. So there's a lot of congestion in the system, okay? Some messages get lost. We need to reinitiate the system, etc. So it takes a long time to really make that happen. And what we work now on in Kings is a very interesting solution where we try to push essentially the data transmission right into the first ping-ponging exchange. Okay, a little bit like the SMS. So the SMS was a kind of a design error on the whole control channel thing. That's why you can have only a certain limited amount of characters, okay? Because nobody thought of using it for that. So we're doing the very same thing now with the data transmission for machines, okay? So it turns out that message 3, the third message I'm sending up to the base station, I can put a lot of data in there. Not unlimited, but I can do encrypted. So suddenly, we can actually bring down the procedure from 2 or 3 seconds to 50 milliseconds. That's already interesting. A lot of stuff we can do there, okay? We came up with some solutions which brought it down to 10 milliseconds. We're not yet at 1 millisecond, but we're getting there. Another interesting thing we work on is on the whole architecture, because very few people will realize that the whole architecture of the cellular world is just a very big elephant, okay? Not sure you know how it works, but it's very simple. In that your mobile phone connects to the base station connects to a so-called serving gateway, and the serving gateway connects to the packet gateway, and then it goes out, okay, to the internet essentially. Now, so far so good, but what you should know is that in 4G, LTE, LTA, you only have about 2 packet gateways and serving gateways in the UK, and they're all in Southern England. So what is the scenario? Refinery in Scotland. I have a sensor which runs on an Orange data plan. My sensor connects to the base station, serving gateway, which is down in London, The thing travels down to London, packet gateway, which happens to be the same box, Cisco box typically, goes out, goes back in, connects to a Vodafone server, goes back into the network, the core network, goes up to Scotland to an actuator to say, hey, you know, there's a problem here, switch off the valve, otherwise my refinery will blow up. Now, we need to do that very quickly. There's a lot of critical stuff we want to solve with machine-to-machine stuff. But as the architecture is built, we can't do it. It doesn't make sense that the data travels all the way down into the country, comes up again, just to switch something off, which is literally maybe like, you know, 10 centimeters apart. But this is where we are today. And we can have an offline discussion later on in the coffee break if you want to know why that is happening. But we're trying to break this now at King's and really try to make it as flat as possible. Because it doesn't make sense for an architecture like that. What we'd love to do is to have the actuator talk directly to sensor to the actuator, or at least via the closest Node base station to really make this communication happen. So I don't want to bore you with simulation results. If you're skilled in this field and you're interested, just drop me an email. I'll send you the latest stuff we have really on the architecture design, medium access control design, etc. So a lot of really exciting things happening there, which I hope, you know, by 2020, 2025 will allow us literally to connect, you know, billions, if not trillions of sensors with very, very low energy budget to the internet. Okay? Now, to conclude, I'd like just to tell you a little bit where the field goes, and I think it's very opportune to do that in this audience here. At King's, one of the things we're driving very much is closing what we call closing the data cycle. Okay, a lot of people talk about big data today. Big data literally means, you know, collecting data, not necessarily large. Could be very large, could be very quick, could be very different, etc. But you're collecting data from sensors, which is what I talked about today. You're collecting data from the crowd, which other people have talked about. You're collecting data from the internet, etc. So a lot of data coming into your engines, a lot of intelligence build up, and then what, right? And then what? Typically, you would just build up, you know, a nice PowerPoint graph, and that's it. So I always said, you know, big data is more for chief executives, essentially, to fill their PowerPoint graphs rather than actually doing something about it. The beautiful thing is to act on the data, to literally do something with that. And here's where the actuation, the robotics part comes in, and you're closing that loop. So that's what we're doing at King's. So we have the sensing guys, telecom guys, artificial intelligence guys, some of them working with NASA on the Mars rover mission as an example, and we have the robotics guys. And suddenly, you know, you can think of the next generation 6G system to be built by robots, designed by artificial intelligence, rolled out automatically, etc., etc. So self-organizing networking going essentially beyond where we are today. So I hope I've given you a nice overview, essentially, or a overview on where we are today with the connectivity of machines, where are the challenges, the mistakes we have done, and the road we are taking. Thank you very much.
Thank you very much.